All right, so we have the concept of open cover, finite covers, and then we have the concept of compact. Let E is a subset of X. We are considering E as a subset of X, and E is a subset of union of G alphas, where G alphas are the open sets in X. Now this E can be basically we are saying that E can be written as union of G alphas, some of the G alphas, not all, but some of the G alphas. Now finite subcover means E can be written by using some of the finite number of open sets, that is G alpha 1 to G alpha n. Hence, from that we can conclude that we call a set a compact set if and only if every open cover have a finite subcover. All right. So this is a concept that we are using in understanding the next theorem that is related to concept of open cover compact, and as well as the concept of relative open sets. Now the theorem says that suppose E is a subset of Y is a subset of X, then we are saying that E is compact relative to X if and only if E is compact relative to Y. Basically we are saying that E is compact relative to X when if E is compact relative to Y. So it is easy to understand the concept. Now for example, I have written and drawn a diagram over here. That is, this is a set Y. A set Y consists of a set E with the open sets V and G. G alphas are the open sets which are there in X as well. So this is a set X, X geometric space. G alphas will, the open sets G will contain outside of Y as well. Now from that we can conclude that E can be written as this E can be written as a subset of union of G alphas, right? Subset, right? It is obviously a subset of union of G alphas, but we know that V alpha can be written as this V alpha is an open set. We can get it by after we do intersect with Y. G alpha, when G alpha intersect with Y, we get this V alphas. So basically this G should not belong over here. So whenever this G alpha intersect with Y, it will become V alpha, and this V alpha will become an open cover for E. So since E is an open cover, E is a subset of this union of V alphas, or basically E is a subset of union of G alphas. Since E is compact, it will contain a finite subcollection. All right. Then from that we can conclude that E is a subset of Y. Since E is a subset of Y, from that we can say that whenever Y intersect with this G alphas that we have concluded, we get that V alphas, which admits a finite subcovering for E as well. Now from that we can conclude that E is compact relative to Y. Now if conversely, suppose E is compact relative to Y. Hence we can say that E can be written as a subset of or the union of G alphas. The same thing, E can be written as subset or equal to union of G alphas, where E is a subset of Y. Okay, I'm gonna continue afterwards. Alright, so as I said, E is a subset of union of G alpha. Conversely, that we are assuming that now from that we can conclude that union of G alpha will act as an open cover for E, and then from that, but we know that E is a subset of Y. Hence we can conclude that E can be written as union of Y intersection. E can be written as union of Y intersection G alpha. E can be written as union of Y intersection G alpha. Since E is compact, we can write union of G alpha 1 intersection Y union J alpha 2 intersection Y, so on up to finite number of times. Hence conclude E is compact. Okay. All right. So next problem that we have here is theorem, that is every compact subset of a matrix space is closed. So it has given that there is a subset of a matrix space K which is compact and closed. So, and from that we can conclude that K complement is open. All right. Now we have to prove it that every compact subset of a matrix space is closed. We just have to prove that it is closed. So for instance, we have a neighborhood endo Q which is inside K. This set is K, and this set right over here, out of this there is K complement. All right, this is compact. That is what we have to prove. Now we have to take a point P belongs to K complement and Q belongs to endo Q, which is inside K. Now the neighbor of Q that we are considering is this endo Q with the radius that is equal to dou, and the radius for endo P with the radius dou, and the distance between this P and Q is equal to dou. So we are assuming that since if it is open, we know that if K is open, we know that the points lying outside all the points will lie inside it. Hence we can conclude that it is open. Now we just have to prove that these two are open sets. This is nothing but the same ideology that we are using over here. Now we are taking a point or element belonging to taking a point or X belong to this endo Q and endo P. All right, from this, but we know that the open sets around this, for example, VQ intersection W WQ VP, let VP intersection WQ will be equal to phi. All right, these are the open sets of containing P and Q respectively, and the intersection of these two will give you phi. But still we are considering there is a point X belongs to this disjoint open sets. Now we know that the distance from X comma P is less than dou. Hence it will belong X belongs to this P neighborhood, since this is the neighborhood of P with the distance endo P. Hence we can say that this X belongs to this, and the distance of X comma Q also less than dou. Hence we can say that X belongs to here and also X belongs to here. And we know that the distance from P to Q is equal to dou. Right, now checking the relation, distance from P comma Q should be less than or equal to P comma X plus D X comma Q, that is less than. Hence we got distance from P comma Q is less than 2 but in the beginning sorry, maybe I have not written okay, here in the beginning I have taken the distance between these 2 points is equal to 2 but what we are getting, the distance between these 2 points are less than 2 so hence we got the contradiction. So from that we can say that this VQ intersection VP intersection WQ is equal to 5. From this we can say that this K is open and K complement is closed. Now conversely assume that we know that K is a compact set. All right, K is compact, so hence we can say that it will have a open cover. Then if it has an open cover and it is compact, then we can say that it will have a finite subcollection. All right, so basically we can say that K is a subset of for a point Q for a point Q belongs to WQ. We are just considering K is compact, right? So K can be written as union of WQIs. Since it is compact, we can write it as finite subcovers Q1, Q2, so on, QK, finite subcovers. Right? Alright, now now similarly we can write for P belongs to VP. It will also consist of finite subcovers like this one. All right, so if we are considering a point X belongs to this VQ over I intersection J, then that implies X belongs to this and X belongs to this. So this is the contradiction, hence we get that the contradiction even though if we know that the intersection of these are empty. All right, okay, next problem that we have is every closed subset of a compact set is compact. Basically this is a metric space. K is a closed set and it is compact. This is F complement. This is compact subset of K. F is closed given. All right, basically it is given that F is a subset of K is a subset of X. All right, here K is compact. We have to prove that V is also compact. All right, now F can be written as union of V alphas open sets. All right, it will become an open cover for F, and we know that K can be written as F union F complement. All right, we know that F is union of V alphas union of F complement. So since since K is compact, given a finite subcover exists. Alright, that is V alpha 1, V alpha 2, V alpha 3, so on, V alpha K with F complement. Hence K is a subset of V alpha 1, so on, V alpha K union F complement. Alright, hence from this we can write, we know that F is equal to F intersection K. We know that F is equal to F intersection K, and we know that K is given by V alpha 1 union, this is union, alright, V alpha union V alpha K union F complement. Alright, F equal to, hence from this we can write F is equal to V alpha 1 intersection F union, so on, union V alpha K intersection F union we get 5 for that. F is a subset of V alpha 1 union V alpha 2 union V alpha K. That implies F is compact. That is simple. Alright, what we did, we use this K which is given condition, and we know that F can be written as union of V alphas. Some V alphas which are the open cover open sets in G alpha, and after that we have K can be written as, since K is compact, we just we just prove K is compact. Since F is a subset of K, we get that F is a compact set. Hence K is equal to F union F complement. Hence we get that K is equal to F union F complement, and then K is equal to union of V alphas. We know that F is equal to union of V alpha union F complement. Since K is compact, the above cover open cover will have a open cover finite subcover V alphas union F complement. Hence we know that F can be written as F intersection K. F can be written as F intersection K, means the points which are there in F, that is V alphas, will intersect with K, will get F intersection K. So we get that K equal to V alphas union F complement F intersection. We are multiplying, we are intersecting with all the elements, and then we get that F complement intersection F. You will get phi, since there is no other element that could belong to this. Alright, now from there we get that V is a subset of this finite subcover. From there we can get that F is a compact set. Since we get finite subcover and also open cover in the beginning, we get that F is also compact. This is open cover. Alright, now next problem that we have here is from that we can also say that F intersection K, this one F intersection K is compact, right? Since F intersection K is nothing but F. So whenever you will get a question like this, if F is closed and K is compact in a metric space X, then F intersection K is compact in X. Because F is closed, K is also closed, then F intersection K will also be closed, and F intersection K will be a subset of K. Since K is a compact, K is compact, we get that by this theorem that F intersection K also compact. Alright. Alright. Next theorem there is, if E is an infinite subset of a compact set K, then E has a limit point in K. E is an infinite subset of K and K is compact, so hence we can conclude that E has a limit point in K. E consists of a limit point. Now since E is infinite subset, we know that if infinite subset will always be closed, and also compact set, it means it will have an open cover and subcover and finite subcover, and also we have if infinite, there exists a limit point, right? If E is finite, then there will be no limit point exist. Hence we have to keep that in mind. Now we are using K, and since K is a compact subset, K is a compact subset of X, basically K is a compact set, we get that K can be written as union of V. K can be written as VQ, union of VQ, right? It will become an open cover for K. Hence K is compact, right? K is compact implies K can be written as finite subcollections of open sets VQN. Alright, we got finite subcollection, and E is a subset of K, we know. Alright, and we know that VQ contain at most one point of E. Now from there we can conclude that E can be written as VQ1 union VQN. That implies E is finite, since it can be written as finite union of subcollection. Left hand side, here left hand side is infinite, that is not equal to finite, hence there is a contradiction. So hence E cannot be written as finite union of subcovers. Alright, hence we can conclude that E has a limit point in K. Actually there is big confusion here. That is if E is infinite, then how come E can be, this is what we know, right? If E is infinite, alright, how come E can be written as union of finite subcollections? So this is we know that implies that E cannot be written as union of finite subcollection. Hence there are some points of E which exist in E, means which exist in open cover, that is open cover union of VQs, which is not finite, it could be infinite. Hence from this we can say that E has a limit point in K. Okay, by this I have completed almost all the concept, all the related theorems to compact sets, open cover, finite subcovers. Hope you understood those theorems. I have just given the brief explanation for each theorem. You can find the systematical or procedural step-by-step guide in your textbook from where you can follow and understand it in a systematical way. Then we have some more concept that is left out, that is K cells. Alright, and then we are dealing with the relation between K cells and the compact sets, and this will be the end of the concept of compact sets. And the next video, hope I would cover perfect and connected sets. This is pretty much easy. Alright, so in this we use Cantor sets, and Cantor set is very much easy. Separated sets and related theorems. And the last topic will be upper and lower limits of sequences. This is pretty much easy, everyone can do it if understood. So it will use the concept of Cauchy principle, convergence, limit points. If you have a good base or strong base in your previous classes, then you can easily understand this. This is pretty much easy. So I thought that I should cover these topics, but I don't think so. It will be difficult for you to understand, but still, if you have any doubts in those topics, if I know, I could help you out. And thanks for watching the video, and hopefully that you people like it. And if you like it, please share with others. And thank you very much. Bye bye.